Welcome to Chemistry Online. Today we're going to talk about chemical equilibrium. Let's start off with a very simple demonstration of the equilibrium phenomena. What we're going to do is start off with a vial of dinitrogen tetroxide, which is essentially colorless. Over time, we note that this vial darkens and we wind up with something like this. Now that's not surprising because dinitrogen tetroxide can decompose to 2 moles of NO2, and NO2 is brown. We start off with dinitrogen tetroxide, we wind up with NO2. However, if we look at this vial and do an analysis, it's not pure NO2. It's a mixture. And if we wait and wait and wait and wait and wait, the composition of that mixture does not change. Now we can do this in reverse. If we start off with NO2, the vial lightens over time. Again, it's a synthesis reaction. But if we look at our composition, once again, we have a mixture. And this is exactly the same mixture that we got in the previous slide. So what we have here are two reactions going in two different directions. We have the decomposition of N2O4, and we have a synthesis reaction where we're taking NO2 and we're making N2O4. This is a system at equilibrium. We show this with our double arrow, and the important thing to note here is that regardless which direction we started the reaction, we wound up with exactly the same mixture. Now that means that when we're at equilibrium, the rate of change of our reactants and the rate of change of our products has to be zero so that we have a constant ratio regardless which way we start the reaction. Now we can show this better perhaps with this simple plot. Here we're going to start with pure N2O4. We're going to let it react to form NO2. As the NO2 is formed, it will then react to reform N2O4. As a function of time, it looks like this. Now when we have a curve like this, we can go to any point on the curve and draw a tangent. The tangent that we draw, in this case for NO2, simply gives us the rate of change of NO2 as a function of time. That's what the slope gives us. Well, let's look out here at this end of the curve. Here our slopes are zero. The fact that we have a zero slope means that the rate of change of each of these is constant. Now, it doesn't mean that their concentrations are zero. It doesn't mean that the reaction has stopped. It simply means that the rate of change of each of these is zero. Now, what we can do is to take some data from this plot and we can adjust, in this case, the partial pressure of NO2 and simply measure the partial pressure of N2O4. When we do this, we get a nonlinear relationship, looks like this, and we can fiddle with it and try to find a way to linearize it. Turns out that we can linearize it because this is an exponential relationship. That is, the pressure of NO2 squared is going to be directly proportional to N2O4. We're going to change our proportionality to an equal sign and a constant, and simply solve for our constant, and this is what we get. This K, this constant, is what we refer to as the equilibrium constant for the reaction. The equilibrium constant for the reaction, this guy, allows us to calculate the ratio of NO2 and N2O4 under any sets of conditions. This is a simple constant. Now, the process of linearizing the curve and coming up with a relationship actually is simplified by what we call the law of mass action. That tells us that the expression for K is simply going to be based on the balanced chemical equation. Let's take the partial pressure of each species raised to the power of its stoichiometric coefficient. If we have more than one reactant or product, we're going to multiply these together. So, for our N2O4 to NO2, our products here are NO2. The product always goes in the numerator. Our coefficient is 2, therefore we put in the partial pressure of NO2 squared. Our reactants here go in the denominator. We have a coefficient of 1, so this is simply the partial pressure of N2O4. If we had nitrogen and hydrogen reacting to give ammonia, our products go in our numerator, so this is going to be the pressure due to ammonia squared. In our denominator, we will have our reactants. Our coefficient here is 1, so this is simply the pressure due to nitrogen. And we're going to multiply that by our other reactant, that's the pressure due to hydrogen, cubed. This allows us to simply look at a balanced equation and immediately write an equilibrium expression. Let's do that for a couple problems here. PCl5 decomposes to give PCl3 and chlorine at equilibrium. Our equilibrium expression, we're going to have our products in our numerator. Both of our coefficients are 1, so it's just going to be the pressure of each of these multiplied together. Our denominator is going to be the pressure due to PCl5. Again, our coefficient is 1. Our next one, our numerator is going to be the pressure due to chlorine multiplied by the pressure due to NO squared. We're going to divide that by the pressure due to NOCl squared. It's very important to be able to write these because this is going to be the first step in solving every equilibrium problem. For example, we are given chlorine trifluoride at equilibrium with chlorine and fluorine. We are given partial pressures for all of these guys, and we want to determine K. Step 1, we have to write our expression. Our numerator would be the pressure due to chlorine multiplied by the pressure due to fluorine cubed. Our denominator, the pressure due to ClF3 squared. Now all we have to do is substitute. We punch this in our calculator, and our equilibrium constant is 5.54 times 10 to the minus 2. There's a tutorial based on this. Here we are given a set of concentrations, or atmospheric pressures, We're given a balanced equation, and we simply have to solve for K. What we're going to do here is to write our expression for K. Well, it's going to be pressure due to hydrogen multiplied by ICl squared. Our denominator will be the pressure due to iodine, our pressure due to HCl squared. We're going to substitute in all our values. Simply do our math, and our equilibrium constant is 0.454. Actually, this does have units of molar, but we never put units on equilibrium constants.